everyone. Great news. I brought my pen today, so that means no finger painting or having to deal with that. I also brought the duck. He's here. I'll attempt to use him. We're going to see if it works the way I hope it to. This is good. I burned my Hawaiian pizza today. I should have used aloha temperature. Aloha. It's Hawaiian. That's a good one. I like that. That's terrible, which makes it good. All right. So today we're going to get through momentum. We're actually probably going to get through most of momentum, if not all of it, which is great. And this is not with me rushing either. We're not like trying to rush through all the content, but the nice thing is we're able to move along nicely. And any extra time we have is just extra review time. So it's great. Now to that end, I can finally show you all the one question that everyone missed, 80% of students missed. We're finally at the phase where I can show you, and it was draw the free body diagram for an object in the air, moving to the right. There you go. All right, I want you all just to try this problem with no options given. Draw the free body diagram for an object in the air, moving to the right. Something here. Demo duck, draw it. There it goes. Draw the free body diagram when it was up here, when it was up in the sky. Yeah, there is air resistance. Do not ignore air resistance. The problem actually specified that. Do not ignore air resistance. And I think that was bolded and underlined. All right, so you go through, you draw your free body diagram. There it is. There's demo duck. All right, so you just go through your checklist. Is gravity acting on it? Yes, like always. Gravity's always acting on things. Is there anything pushing or pulling it? No. There is no applied force. There is no applied force. And that was the most common mistake that a lot of people put. They put if it's traveling to the right through the air, there is an applied force. That means something's pushing it. So my question to you is, what's pushing it to the right in the air? Nothing. Nothing. There's no rockets attached to it. There's no propellers attached to it. There's nothing pushing it through the air to the right. Is there a normal force acting on it? No. It is not sitting on the surface. If it's on a surface, if it's leaning against something, standing on something, resting against something, yes, but it's not. Is there air resistance? Yes. And this is where it might have been a notation thing. I did call air resistance friction. That's a pretty air resistance is another form of friction in a lot of ways. It slows things down. It's opposite direction of motion. So that's fairly common. But maybe moving forward, if I give a problem like this, maybe I'll call it like air. But they're the same thing. F air. And that's the answer. That is the free body diagram for an object traveling through the air. I do not care what the object is. Now, I did have to specify that it's traveling to the right. If I did not tell you the direction, if I said, what is the free body diagram for an object traveling through the air, it's impossible. You have to know which way it's going because friction is always opposite the direction of motion. So I made very clear in the problem, when it's moving directly to the right, friction is to the left. If it was opposite, if I said, what is the free body diagram for an object moving to the left, then it would be the other direction. So this is, you can almost guarantee that there will be a problem like this in the final. Because if this many people missed it, it means I didn't do a great job of covering it. So great, now I've covered it again. So now I'll test you all on it again, and we'll see how that goes. That was the one major thing that I didn't do a great job of, and so I'll need to give you all more free body diagram. I say give you all. In the future classes, I will need to get through my diagram stuff. Also, for good or for bad, I did find out which class I'm teaching in the spring. It is not Physics 2. So I am teaching 2053, which is the Physics 1 for non-engineers. So in case you're curious. There you go. That was a question that variety of people asked. Okay. So I think that's it. All right. So let's start solving momentum problems. We'll see how many problems we're able to solve today. We will either be able to solve all of them or at least most of them. Whatever we don't finish, we'll finish Tuesday and then we'll start gravity. Okay. A 75 kilogram person is riding in a car moving at 20 meters per second when the car runs into a wall. Calculate the average force on the person if he is stopped by a padded dashboard that compresses an average of 1 centimeter, and then do the calculation if instead they're stopped by an airbag, and that compresses 15 centimeters. I'm going to tell you, you can see the answers here. The answers are a little exaggerated, because the reality is the padded dashboard is not the only thing that would stop the person. If they're wearing a seatbelt, that's going to factor into things. The friction from the seat, that's going to factor into things. So to that end, the way this is set up is as if the dashboard is the only thing that stops the person, and only over that compression of 1 centimeter. And so the answer is like ridiculous large. So the answer is unreasonably large. I want to point that out. But I do also want to say that with the caveat that the whole point of this is just to show how much of a difference the answers are. In order of magnitude. Even the second answer is so large that like it's not healthy. The airbag is also not a healthy force, and that's because we're assuming like this is the only thing stopping. That basically they're getting stopped over this compression, and that's not the reality. The car is also crumpling. There's a lot of things going on here. So really, the takeaway from this problem isn't so much the result as a meaningful answer, so much as how to solve the problem, and then just comparing these two values. So whatever. There you go. There's my big caveat. These answers are not realistic. But solving the problem, it is worthwhile. And go ahead and try it. There are 3 ways to solve this problem, and I will show you all 3 ways. I'll only work through one of them for the sake of time. But yeah, you go and figure out how to solve this. And if you do, great. See if you can figure out the other 2 ways. So, first step is what's given. We got a mass of 75 kilograms. We have an initial velocity of 20 meters per second. And we have a final velocity of 0. Because you hit a wall, you stop. It also says they stop. Okay, and then this variable, centimeters, we're going to call that delta x. That is not my final position. That is not my initial position. That is the distance. That is a change in x over which all this is happening. And I'm immediately going to put this in scientific. I'm going to immediately convert this. I like to convert things this way. You can do 0.01 if you prefer. Just don't leave it in centimeters. All right, we're solving for the average force. And then, step 3, give you all a few moments. There's 3 ways to solve this. One of the ways, I could have given you all this problem on the first test. Is my hint for one of them. But the other 2 are the ones that, from what I've taught you so far. Feel free to chat with people next to you. So quiet. Anytime I give you a problem, feel free to check with people next to you and talk. In fact, I prefer it. All right. So the first way you can do this is F equals ma. That's right? Right, there's force. We know mass. And then the question goes, but I don't know the acceleration. You can find it. Vf squared equals V naught squared plus 2a delta x. Kinematics equation. Great, that's one way to do it. Again, I could have given you all that on the first test, and it's totally doable. All right, second way of doing this is, and we're going to go in the order I taught you all these things. The work done, so anytime you'll see average force, that means it's a constant. And so we have a constant force. Work equals force times distance times, we can say cosine theta if we want to. That's fine. And great, okay, then the question comes down to what's the work done? All right. I'm going to start using this equation more because I like it better. The work is equal to the change in energy. So what's doing work in this, or what energy is present here? Only kinetic. Kinetic is the only type of energy present. So we get that the work equals 1/2 mv final squared minus 1/2 mv initial squared. Great, that's another way of doing this problem. I've got m, I've got f, so I got v, final and initial, I've got the distance, that's just delta x. Do note that our final velocity is 0 and our initial velocity is 20, so you get a negative. But our work will also be negative because it'll be cosine of 180. Why is it cosine of 180? The force is this way. They're moving to the right. So that's why that works out. Okay, that's another way. And then the last way is we can use the equation I gave you all last class, which is that the average force equals mass, let's write it this way, change in momentum over change in time. So I introduced that to y'all with momentum, which equals m delta v over delta t. So great, I know the change in velocity, I know the mass. How do I find the time? Kinematics. So there's an equation in kinematics that says xf equals x naught plus vf plus v naught over 2 times the time. It's the average velocity times time plus my initial position equals final position. Xf minus x naught is delta x. So you can rearrange that to make it maybe look a little nicer. There we go. And all these work. All of these work. Which way am I going to solve it? I don't know. I guess I'll pick the middle one. I don't know. It seems like the easiest one. Is there a best way to do it? No. They're all right. They are all correct. Neither of these are better than the others. Rule of thumb, the best way to solve a problem is the way that gets you the right answer. That's it. You can maybe argue efficiency, but you often spend more time trying to figure out the more efficient way than just if you just pick one and do it. Yeah.
So the middle method, you said the theta 180.
Yeah.
Or referring to the force as the dashboard.
Yeah, think if your face hits the dashboard, you're moving to the right, but the force will be to the left. Yep. Yeah. We'll leave that beautiful picture there of someone's face hitting a dashboard. All right, so yeah, I'm just going to pick this one. It doesn't mean it's the best way. The star does not mean the best way. I just got to put something so people look at this in the future. They know which one I'm doing. Okay, so work equals 1/2 times, okay, let's just actually cancel this out. That's 0. The final velocity is 0. I'm going to save myself some handwriting. So work equals negative 1/2 times 20 times, nope, wrong spot. 75 times 20 squared. That equals a number. Calculator is here. But yeah, you'll find if you solve this problem, all of them get you the same thing. So that's kind of nice, right? If they didn't get you the same thing, that'd be very concerning. All right, so we get the work equals negative 15,000 joules. Great. So that's this right here. And then I'll color code the next one. I'm going to use this right here. Mark it off to the side. So negative 15,000 joules equals the average force times my delta. This distance here is delta x. I'll chuck that there. 0.01 times negative 1. I put the angle there as cosine of 180, so that's already labeled. Delta x. You do some math. Divide, the negatives cancel. That's good for us. And yeah, look, we got the right answer. Woohoo. 1.5 e to the 6 newtons. Again, this answer is nuts. Like, this is completely ridiculous. The answer makes, given the numbers we have, the answer makes sense. If you are traveling 20 meters per second, remember 27 meters per second is 60 miles per hour. If you just remember in your head like 30 meters per second is roughly 60 miles per hour. Again, that's useful. You're going about 40 miles per hour, and you stop over a distance this big. Yeah, like that's, of course, it's going to be an insane force. The amount of force required to stop something that's going 40 miles per hour over 1 centimeter, like that, yeah, you need an insane force to make that happen. So again, this problem is not realistic because the car itself is crumpling. So there's some extra distance there from the crumple of the car. There's some extra distance because you're in your seatbelt and you're kind of getting pulled forward and slowed down by that. So that's why we're not taking into account all of these things. And that's why our answer is not realistic. But it is still a good exercise in using, hey, there's 3 ways to solve this. And if you change the distance, the last step is the only thing with distance in it. The bigger the distance, the smaller the force. So that's the takeaway here. The math part's still good. The final result is but it gets the idea across. All right. There you go. We didn't actually use momentum at all, but you know, it's there if you want to. Don't worry. We'll spend the rest of the class doing momentum things. You'll get plenty of practice with momentum. Okay, so speaking of today, I need to delete all the work on here. I thought it was deleted, but clearly it's all down here. See all this work that we're going to do today? Here, where's the foreshadowing? Where's the bad one? All right, here you go. This one takes 3 slides for me to work through. Not because the physics is hard. Not because the physics is hard, but because the math is tedious. But I will work through it. We will suffer together. Oh, I can't delete it all. All right. Jank solution. I copied these over. So anytime I teach my studio course, I copy the slides over because I often make new clicker questions and I don't want to. So we just, boom, put them here. I got to delete all the stuff. What? That's so weird. It is ink. Oh, silly me. Silly me. All right. There we go. Okay. And now these go back over here. Woo! All right. Fantastic. We did it. And yeah. So, where is it at? Great. That's a little too soon. Move that down. All right. This is all we're doing today, y'all. This is it. Add up all your momentums in the beginning, it equals all your momentums at the end. We're going to spend the next hour or so doing problems with this. This is the equation. Add up all your momentums in the beginning, equals all your momentums at the end. It is a vector. This is an incredibly powerful tool because it works for every single problem as long as there's no friction, air resistance, as long as no work is being done. As long as specifically due to like friction, air resistance, or someone pushing the box. I'll give you all an example on this slide. Like I'll show you an example of obviously why this doesn't work if there's friction. It'll be really simple to see that. As long as there's no friction, as long as there's no air resistance, as long as there's no someone pushing it. Long story short, as long as my energy stays within the system, it can split into a million pieces. My system can blow up. That's fine. Now my system is just a million pieces flying around. Who cares? As long as it doesn't enter into the environment, this works. So like, for example, this equation, you can use this for a rocket. If you calculate the momentum of all the gas particles flying out the bottom of a rocket, so a rocket sits at a launch pad, no momentum. If you calculate the momentum of all the gas particles shooting out the bottom, it will equal the momentum of the rocket itself, based on this equation. If you have an asteroid in space and it blows up into 10 different pieces, the momentum of the asteroid to begin with will equal the momentum of all the pieces that split off from it. It doesn't matter how it exploded. It doesn't matter if pieces flew off at different times. It doesn't matter. This holds as long as you don't lose an energy to the environment. So it's really, really cool. This also works if you have like something squished. If you have like a bullet and it hits something and that bullet gets absolutely like squished and flattened and whatever it hits also gets kind of squished or whatever, conservation momentum still works. If I throw a thing of Play-Doh at this whiteboard and the whiteboard started rolling, it works. It doesn't matter if your stuff deforms. It doesn't matter all these things. All that matters is energy doesn't leave your system, and this works. So it's super, super useful. All right. Quickly remind you all, P equals MV. So two things I want to remind you all on this slide. So if you have X and Y components, this splits. You have to add all your momentums in the X equals all the momentums at the end in the X. So reminder to you all, I'm just mentioning this now. I'm going to mention it to you all like 10 times today. These are vectors. You got to keep them separated. You got to keep the X and the Y separated. What is really cool with momentum is if you know the initial velocity and you know the final velocity, you can like use the magnitude of velocity. If you know that for all the objects, it also works as a collective, which is kind of cool. But if you want to find the X and Y components, you gotta keep them separated. All right, great. That's one thing. X and Y are separated. Don't forget that. Like, beat that into your all's heads because you need to remember that for lots and lots and lots of things in life and your future classes. And then the other thing is, I told you I'd give you an example why this doesn't work with friction. I got a box, and this box has some initial velocity. Let's just call it 4 meters per second. And let's say there is friction, and eventually the box stops moving. It's sliding, and then it eventually stops. Let's just quickly see that momentum doesn't work for this, conservation momentum. Let's make the mass of this 1. That's a nice number. The mass doesn't change. All right, so what's my initial momentum? MV initial. Great, what's that going to be? 1 times 4. So my initial momentum is 4 kilograms meters per second. If it's not moving, what's my final momentum? 0. Obviously, 4 does not equal 0. So that doesn't work. If you lose energy to your environment, then you can't use this. If there's friction, there's air resistance, you can't use it. All right. So that's the big caveat to this incredibly useful tool. We're going to do a bunch of problems today with this. Incredibly useful tool, but you cannot use it if there's air resistance, friction, or things like that. At least not once you're acting on it. So, all right, cool. Okay, I'm going to mention this now. There's 2 types of collisions. Let me actually show you all this slide first, and then I'll show the other one. So when do we use it? When things bump into it, when there's collisions or separation. A separation is just opposite of a collision. So when 2 things either hit each other or you have something that's together and it breaks apart. We have two types of collisions. We have elastic and inelastic. Elastic is really just a special case. Elastic collisions are where they bounce off each other perfectly and all mechanical energy is conserved. All kinetic energy is conserved. Okay, that's an elastic collision. There is basically only two types of problems I can give you with elastic collisions, and it's always like the pool billiard balls. Yeah, the game of pool, they're really hard, rigid objects. That's basically the only time elastic collisions happen. The reality is you need something really, really, really rigid that when they bounce off each other, there's no crumpling, there's no squishing, none of that. So billiard balls are like the Newton's cradle. Those are like the only elastic collisions, perfectly elastic you'll find them. Those are the easiest examples I can give you. Otherwise, almost anytime things run into each other, there's like squishing happening. In which case it's some kind of inelastic combo, whatever, it doesn't matter. That's fine. You can use conservation momentum if things squish. That's fine. Again, I could chuck a piece of Play-Doh at something and I could use conservation momentum for that. That's fine. I could have a piece of dynamite and have it blow up into a million pieces and I could use conservation momentum for that. That's fine. But elastic, we're going to do the problem with elastic, and that's the one that's going to be mathematically unpleasant. It's the best way to put that. You'll see when we get there. All right. Inelastic, this is the punchline. Inelastic energies, I already mentioned this. The energy you start with is the energy you end with. That's true only in a perfectly elastic collision. Is this true? Okay? So, I think we can finally, kind of all I need to show you, and now we just get to practice it. That's fun. But this is our bread and butter, y'all. Like, that's just all we're going to be doing for the rest of class. It's a good time. All right. I have two objects, M1 and M2, which each have their own velocity, V1 and V2. What's the total momentum of those two objects? Is it M1 plus M2 parentheses times V1 plus V2 close parentheses? Is it M1 V1 plus M2 V2? Is it M1 V2 plus M2 V1? Or is it M1 plus V1 plus M2 plus V2? What is the answer? All right, we'll go for 10 more seconds. And 5, 4, 3, 2, 1. Boop. Okay, what's our total momentum? So, we could say this is initial. We could call this our initial side. So we could say, hey, what's our total momentum in the beginning? What's our sum of P initials? Let's just pretend like it's initial for the sake of it. All right, so it's, P1 initial plus P2 initial, which equals M1 V1 initial plus M2 V2 initial. I know these don't have initials, but let's just pretend like they do. Boom, there it is. Yay, you did it. You added up momentums. That's what we're doing today. And that equals whatever's at the end. So you just set up your problem. What do I start with? What do I end with? Add up all the ones at the beginning equals all the ones at the end. Great. Okay. So, just like we said, you just add them all up. And then you add up all the beginnings, and it equals all the ends. That's what we're doing today. It's like energy. But it's just all MVs. MV, all the MVs. Nice and straightforward. Just don't forget, y'all, x and y components. Don't forget it. Okay, great. I had two objects separated, but what if they get stuck together? What's their new mass? Two objects, they hit each other, they get stuck together. What's the new mass of that object? That singular object they've turned into? Ten more seconds. And 5, 4, 3, 2, 1. Yeah, so we have our two objects, and they were separated. So let's pretend like we had a situation like we had before. This is my initial. Two objects heading towards each other. And then final. They're stuck together. What's the mass of that? They get added. Makes sense, right? If something has a mass of 2 kilograms, something has a mass of 2 kilograms, they're together, it's 1. Great, you all got this. Fantastic. All right. So let's put all of this together. We're just building a conservation momentum problem, just showing you how straightforward this is. I have two objects, m1 and m2, with velocities v1 and v2, like the first problem I gave you. That's how they start. They then hit each other and get stuck together and end up with a velocity of v3. Build an equation for conservation momentum. Conservation momentum is very much a build your own equation. Just like conservation of energy, build your own equation. Is it m1v2 plus m2v1 equals m1v3? Is it m1v2 equals m1v3? Is it m1v1 plus m2v2 equals parentheses m1 plus m2v3? Or is it m1v1 plus m2v2 equals m1v3 plus m2v3? All right, we'll go to like 210. Or 110, I don't know if I said 210. All right, 5, 4, 3, 2, 1. So remember, it's a build your own equation. Sum of initial momentums equals sum of final momentums. What momentums do I start? We draw a picture. We draw a pretty picture up here. You got an object here. What's interesting? Doesn't matter if they're going towards each other. Who cares? They can be going the same way as long as my objects eventually collide. If this guy's going fast enough, they'll collide. It doesn't matter whether or not they're going the same direction or opposite directions, as long as they collide. Now, you do need to be careful with positives and negatives, y'all. These are vectors. We do get directions from the picture now. The math doesn't tell you the direction. The picture does. Sorry, the math doesn't tell you the sign, positive or negative. The picture does. Okay? So just keep that in mind, y'all. When you're plugging in stuff, don't forget to do that. Anyway. So M1, V1 plus M2, V2, they get stuck together. There it is. Now, these two answers are identical. That's just to remind you all, if you have two objects stuck together, they're going the same velocity. This bottom equation says that in a different way. That's just to show you all they're the exact same thing. Pick your poison. I generally recommend C. That's a better way to write it, but they're both the same thing. Anyway, all right, fantastic. All right, So like I just said, things get stuck together. And just to make this point now, two objects getting stuck together is the exact same problem as an object stuck together getting split apart. Just opposite. Okay? So we're going to see momentum problems with that, where instead of two objects hitting each other and getting stuck, the exact opposite happens. They start all together and then they spread out. An example of this is literally anything exploding. Anything exploding, you can use conservation momentum for. It doesn't matter why it breaks into a million pieces. It doesn't matter if there's like an explosive in it. It doesn't matter if the explosive is big. It doesn't matter if the explosive is small. You just take the initial momentum of your object equals the momentum of all the bits and pieces that fly off it. All of them. When things explode, there's a lot of pieces. Yep, I think that's all I need to say about that. All right, this next slide I'm going to show you. Please, on this next slide, I'm going to give you examples of equations. Do not memorize these equations. These are kind of templates. You should always kind of build the equation. You should always basically be building the equation from this. Sum of momentum's initial equals sum of momentum's final. That's an M. Please always build it. I'm going to show you all the next slide is like some examples of like various scenarios. But if you just write down these equations and you only use these equations to solve problems, you're going to run into a situation. The next ones only have two objects. What if I give you 5 objects? I don't want you to end up in a situation where you're like, I have no idea what to do. This equation works for any problem I ever give you. The following equations only work if there's 2 objects. So they're just templates. They're just to give you examples. So case in point, if you have 2 objects colliding, object 1 and object 2, if it's an elastic collision, they bounce off each other or, whatever, they're going to bounce off each other. And then you have M1 V1 final and M2 V2 final. It's just to show you examples of sum of momentum initial equals sum of momentum final. That's the only purpose of this slide. It's not to give you equations that will be on a formula sheet because they're just templates. Great. So 2 objects that bounce off each other. Fantastic. This one down here is an example of 2 objects that start separated and then they end up together. You all actually just told me that. And then the last equation is an example of the exact opposite. 2 objects start together and then they break apart. It doesn't matter why they break apart, as long as the reason why they break apart is contained within the system. If something external hits them, then you have to account for that. But you could. If you, for example, had a system, a rock, and someone shot a bullet at it, and the bullet hits the rock and the rock splits. If you wanted to make that problem, and it split into 2 parts, you would just then add another object. Let's call it M3 V3 initial plus, and then the bullet would bounce off it and go somewhere else. Woo! You can have all the things. You can have something together and then something hits it, whatever. This is the bread and butter, y'all. Now, you're starting to see that the subscripts start to stack. We have a velocity 1 initial. Well, just be prepared. You're going to start to see velocity of object 1 initial in the x direction. All the subscripts. I warned you all about this way at the beginning. So many subscripts. But you need it. You need every subscript to be able to describe it. We'll get there when we get there, but great. Okay? So anyway, don't memorize these. That's not the purpose of these. These are templates. Just to show you what it looks like to set up these equations. Okay. So then just, hey, how do we solve these problems? It's really straightforward. Draw a picture. If there's a collision or a separation, it's conservation momentum. That's and then, you just go through the classic, y'all. So these problems are very much hey, there's a collision. Draw a picture. Write down your givens. Write down your missing. If there's a collision or separation, immediately when you all get to step 3, it's got to be this initial momentum equals final momentum. If 2 objects hit each other, momentum is almost guaranteed to be a way to solve And then don't forget to split things in X and Y. All right. And now we practice. Conservation momentum is very straightforward. You'll see that as we solve these. It's all kind of the same thing again and again and again and again. So really, these, if you're just careful, these problems are very straightforward. There's no tricks to them, really. There's one tiny little thing. We'll see it when we see it. Okay, two-figure skaters are coasting in the same direction, meaning they are not pushing themselves forward. They're not adding energy to themselves. All right, the leading skater is moving at 5.5 meters per second. The trailing skater is moving at 6.2 meters per second. When the trailing skater catches up with the leading skater, he picks her up without applying any horizontal force. That's important. Again, he's not adding energy. He's not taking energy from the environment. No work is being done. If the trailing skater is 50% heavier than the 50-kilogram leading skater, what is their speed? Bunch of words. Draw a picture. If your picture's bad, your problem will be bad. So they start separated. We draw some arrows. Now, the trailing person has to be going faster, otherwise they're never going to catch up. So the problem tells us that, but it's just good to kind of recognize that you can only catch up to someone if you're going faster than them. Oh, and initials. Don't forget to put initials. You can put I's, you can put knots. If y'all haven't noticed at this point, I'm not very consistent. Sometimes I do this, and sometimes I use the knot. They mean the same thing. I don't really have a preference for either one, which is why you find me going back and forth on them. Various instructors may or may not have preference. Just keep that in mind. If you're like, man, why does he keep doing that? Maybe you didn't even notice. All right, that's my initial. And then final, they're stuck together. And they're moving with some final velocity. I don't need to label this as like 1, 2, or 3. If all the things are stuck together, I'm just going to call it VF. You could call it VF 1, 2, I guess, if you really wanted to. Like, if you want to do that, feel free. But if there's only one final velocity because everything's stuck together, I just don't even bother. You do whatever makes sense to you. Having good notation is really important because otherwise it's easy to make mistakes. And if you ever look at your work in the future, you'll be very confused if you don't have good notation. The classic example of this is if you do programming, make sure you comment your code really well. If you haven't learned that lesson, you will. One day you'll look back at something and you'll wonder, what the heck was I doing? And if your notation sucks, future you is going to be upset at past you. And it's all you. So you're just upset at yourself. So anywho, pro tips, right? All right. V1 initial equals 6.2 meters per second. V2 initial equals 5.5 meters per second. Mass of person 1. So person 1 is, and this is where just kind of more reading comprehension. If the trailing skater is 50% heavier than the leading skater. So the leading skater is number 2, and the trailing skater is number 1. So that's numero 2. That's number 1. So that's 50 kilograms, and person 1 is 75 kilograms. Small thing, but if you make that mistake, the rest of the problem goes out the window. Get the exact numbers. All right, step 2. What are we solving for? V final. Step 3, how do? Sum of momentum's initial equals sum of momentum's final. These are vectors. We are blessed that this is a 1D problem. Don't worry, I'll give you one that's not in the future. And, I guess you do need to remember that P equals MV. All right, build your equation, y'all. Build your equation if you have not done so already. Conservation of momentum and conservation of energy are build your own equation problems. Oh, and the answer's up there if you solve it, so you can check your work. All right, so we just add up our momentums in the beginning. That's M1 V1 initial plus M2 V2 initial equals, they end up together. Ta-da! It's the equation you all did in the clicker questions. You made it. We built it. They start separated, they end together. And now we just put in numbers. Now is the plug and chug part, which is the least exciting. But as engineers, sadly, you all must do this. If you're physics majors, you would be spared this suffering in future years. Physics majors, when you get to later classes, we stop plugging in numbers entirely, and we just get an expression for VF. So like my solution, if I was a physics major, would be VF equals M1 V1 initial plus M2 V2 initial divided by M1 plus M2, and that would be my final answer, and I wouldn't have to plug in anything. Physics care about the problem. Now I can solve an infinite number of problems, but as engineers, you are tasked with actual exact problems, so you must plug in numbers. So I must train you to do so. So we must suffer together. All right, let's plug in numbers. So good. Let's actually figure out what's going to happen in this exact scenario. 75 times 6.2 plus 5 nope, we'll put the numbers in the right spot. 50 times 5.5, all divided by 75 plus 50. You plug that in a calculator and it gives you an answer, which is 5.92. Now, the reason all my velocities were positive is I chose to make the person going to the right. It didn't actually specify. Your answer would have been correct if you said everyone was going to the left. Your answer would just be negative. We do care about direction. We do care about direction. You're going to see examples of that ahead. So I decided to make everything to the right, so all my answers were positive. This answer would totally be valid. Notice how it says, what is their speed? I didn't ask for their velocity, which is why I didn't need to give you the directions, but whatever. Okay. Straightforward problem, y'all. Nice and simple. You set it up, you solve it, easy peasy. Now we're going to enter into the 3-slider. The first slide will be writing the physics, and the next 2 slides will be plugging in numbers. It's good for you, right? It is valuable. There's a reason we're doing it, and I'll tell you why. A boy sleds down a hill onto a frictionless, ice-covered lake at 10 meters per second. In the middle of the lake is a 1,000-kilogram boulder. When the sled crashes into the boulder and is propelled backwards, this collision is a perfectly elastic collision. If the boy's mass is 40 kilograms and the sled's mass is 2.5 kilograms, what is the speed of the sled after the collision? Draw a picture. So you got your boy. He's going 10 meters per second. He's on a sled. And you got a rock. And that rock, and it is not necessarily specified here, but it's not moving. Most boulders you interact with won't be moving. So, we can make that assumption pretty safely. And then the final situation, the boy's going to bounce backwards. V1 final. And the boulder will also move because there's no friction. So it will move. If you run into a 1,000-kilogram boulder in the real world, no, they're probably not going to move because of friction. But if we ignore friction, it will. Yeah. The boy, that is a great question. No, the boy is permanently attached to the sled. Yeah, otherwise this problem's even impossible. He is wearing that. He's so ready to run into that boulder. It's happened to him before. He learned his lesson. All right, so you got the mass 1 is actually going to equal 40 plus 2.5. Let's just go ahead and combine them now and not need to worry about it later. It's a boy and a sled, so you care about both. So great, we've taken that into account. Mass 2 equals 1,000 kilograms. And we know V1 initial equals 10 meters per second. And that's all we know. What are we solving for? We are solving for the velocity of the boy and his sled at the end. And we're solving for two unknowns. Go ahead and build your equation, y'all. Sum of momentum's initial equals sum of momentum's final. Build your equation. And see if you can discover the problem with this problem. All right, so they start separated. So M1, V1 initial plus M2, V2 initial equals M1, V1 final plus M2, V2 final. We are blessed that this term at least goes away. The initial velocity of the boulder is 0. Do you spot the problem with this, though? Is this possible? How many unknowns do we have? How many equations do we have? Yeah, that's a problem. How many equations do we need? 2. So I want you all to see if you can figure out what the other equation is going to be. And this is my hint to you, is you might need to look back on previous slides. This collision is an elastic collision. All right, so let's jump back. What is the magic to solving this problem? Where is it? Not that one. All right, so great. There's conservation of momentum. Here I told you about inelastic and inelastic, and we see something special. Elastic energy is conserved. Energy is conserved. In a perfectly elastic collision, energy is conserved. The energy you start with before the things equals the energy that happens after that. That is only true of perfectly elastic collisions. In elastic collisions, energy is not conserved. If something deforms and it does not spring back, you lost energy. So like Play-Doh, if I chuck a ball of Play-Doh at the wall, that deformation, some energy was lost in that deformation. In this problem, we're assuming these things are perfectly rigid objects that just bounce off each other like billiard balls. It's unrealistic, but it at least lets us solve this problem. So that's why I told you all it is a perfectly elastic collision, meaning we can do conservation of energy. So we ask ourselves what energy is present beforehand, what energy is present afterwards. We get to do EI equals EF. There is no work being done. You can't do momentum if there's work being done. We start with some kinetic energy. The boulder has no kinetic energy, so just the boy and his sled have kinetic energy. And at the end, V1 final squared, both objects are moving. We have two equations and two unknowns, and this is it's not the worst thing. It's a system of equations. Two equations, two unknowns. We are going to solve through it. I'm going to go through all the steps. The value of this problem is one, realizing that elastic collisions can exist, and in which case you get to use two equations. So let's you solve for two unknowns. Great, that's one benefit. The other benefit of this equation is learning to be careful. This problem has a bunch of algebra steps to it. And I will straight up tell you, on the test, I am not going to give you a problem that requires a long time to solve the math. I'm not going to do that on the test. I have a very limited amount of time to test you, and I'm not going to spend a lot of that on math. However, as you progress in your engineering, computer science, whatever classes, the problems are going to get longer. As a physics major, I can tell you that I got to the point where problems would take 1, 2, 3 full sheets of paper. Like one page, then the back, then another page on the front. You will encounter problems like that in your future classes. They will be involved. They will have many, many, many steps to them. Every single step is an opportunity to make a silly mistake. You got to be good at this stuff, y'all. You've got to be you not only need to be able to know the content, you need to be careful. You need to take your time. And so that's the benefit of this problem, is honestly just an exercise in being careful and doing a bunch of math steps for the benefit of making certain you can still do that. If you are taking statics, the entire class is a class on systems of equations. So much algebra. So there is benefit in this because being careful is important. Doing a bunch of math steps in a row and not making a single mistake is a skill that you all need to have. As tedious as it may seem, as annoying as it may seem, trust me, you will encounter it. Guarantee you. Yeah.
The only question I had is that since the boy's sliding down a hill, does he start at the top?
Yeah, it's a great point. So the boy started at the top of the hill, and when he got to the bottom, he got to that 10 meters per second. That was just to tell us how he got moving. Yeah. So there is a beginning before this, but we got what we needed out of that. Yeah. That's a great point. Our initial is kind of some situation where we have enough information to actually do something with it. So yeah, that's kind of extra information. All right, so what am I going to do with this? I am going to do I want to put in numbers yet? Sure. All right. Do I want to do it in variable form? I hate working with numbers because numbers all get mixed together. So I tend to work in variables as much as possible. So what I'm going to do is I'm going to solve for V. Yeah, I am going to do that. So V1 final, I'm going to solve for V1 final in terms of all the mess. So M1, V1, I'm just going to start doing some algebra, y'all. And I'm going to take it slow. Great, I just moved things around. Here, I'll put numbers in. Y'all I think are more comfortable with numbers, so I'll do that. All right, so 42.5 times 10 equals 42.5 times V1F plus 1,000 times V2F. We're going to solve for V1F. I have made that decision. So this is going to be 425 minus 1,000 V2F. Every step I do, I'm going to kind of double check myself. It seems stupid, but look, there's so many chances to make mistakes here. All right, great. I am now going to divide this side by 42.5 to get rid of that. So I get V1F equals 10 minus some number, 20 something. Yay! And you may look and you say, that's not that bad. We got to plug this into here. And it's, again, this is not the worst problem in the world, y'all. This is just a bunch of algebra. But that's the gripe. It's a bunch of algebra. But I will work through it with you all. And I highly recommend you all do this as well. This is a great problem to sharpen your algebra skills. It's not terrible. It's actually, look, this could be much worse. When y'all get to statics, you might have 3 equations and 3 unknowns. Or 4 equations and 4 unknowns. All right, so we're going to move on to this guy. So I'm going to copy those over. I'm literally going to copy those over. I'm not going to rewrite them. Normally you do this on one sheet of paper. I'm doing it on a bunch of slides. There's only so much room. Cool. Okay, so we get 1/2 times 42.5 times 10 squared equals 1/2 times 42.5 times parentheses 10 minus 23.53 V2F squared plus 1/2 times 1,000 times V2F squared. Do a bunch of algebra. All right, you get to FOIL things. Times 100 minus V2F plus 553.66 V2F squared, parentheses. All right, woo. All right, and at every step, I'm rewriting everything, both sides of the equation. That's a very good and important practice to get into. I'm going to go ahead and round that. $11,768. Good. Okay? At any point, if y'all feel like I make an algebra mistake, let me know. This is why you work in groups. Because it's very unlikely that 2 people will make the same algebra mistake in the same spot. All right, so those cancel, subtract them over. Oh, I was wondering, I was like, man, when I solved this before, the numbers are slightly different. One thing I could have done to make my life a little easier I could have canceled out all these 1/2s. It would have been one less number to plug in, but I didn't. So here I am. Trying to erase there we go. So whatever. I was like, man, when I worked this out this morning, the numbers are slightly different. Whatever. It works out the same. It doesn't matter. Math is math. If you're doing the right rules, it still works. So you add those together. And hey, something nice. You are blessed that you don't have to do the quadratic formula. One of the V2Fs cancels. So 10,000 equals 12,268 V2F. So V2F equals 10,000 divided by that, and we get the answer. And we did a good job. Yay. That's it. Bunch of algebra. There is one immediate check we can do without having to check all our math again. There's one check we should do. Does the sign of this make sense? I said it's positive, which means I'm moving to the right. Is my boulder moving to the right? Yes. You should check that. Why do I say that? Because I made that mistake this morning where I misplaced a negative sign and my answer was negative, and I was able to make that check and realize I messed up somewhere. It's a very easy check that you should do. A difference between a positive and a negative, again, it seems so small. Just one symbol. But the difference between positive and negative in the real world means either a rocket going up or a rocket going down. Like, it can be a lot of money if you mess up a positive or negative, or it can cost lives messing up a positive or negative. Even though it seems really, really tiny, a positive answer and a negative answer are going to the right. Your car being in reverse or your car being in drive are vastly different experiences. Don't mess that up. All right. There is one last step that we need to do. Yep, just plug it into that relationship that we have. So let's do that over here. So V1F equals 10 minus 23.53 times 0.815. You plug that in. And you get negative 9.18 meters per second. We ask ourselves, does that make sense? Does a negative velocity make sense? We look at our picture. Yeah, the boy's going backwards. That's good. That is an easy, quick check that you should always do. Does my answer make sense? Check your positives or negatives. Let's see, we got 10 minutes, so I think we can at least set up the next problem. And then we'll actually plug in the numbers next time. Okay. Oh, let me document this to y'all. So this is an elastic collision, y'all. It's gross. Ironically, an elastic collision is the worst one, the one where they bounce off each other, because you get more unknowns. This next slide, I am not going to derive this. Okay, so a reminder to you all. I will not give you all a problem like this on the test. Not because it's a bad problem, but because I spent like 7 minutes doing math, and I spent like 3 minutes doing physics. Rule of thumb, any problem I give you on the test, 70% of your time should be physics, 30% of the time should be math, kind of on average. If you're spending most of your time doing math, something's off. Okay? So keep that in mind. I test you all in physics, not math. You get plenty of math classes. But I will point this out to you. It turns out if you have exactly two objects, like we did in our problem, we set this up. We built these equations. You can watch this video on your own time if you want. If we have these two equations, conservation of energy, conservation of momentum, perfectly elastic collision, you get this really cool relationship. They do a bunch of math tricks, and you get this really cool relationship that if you add up the velocity of object 1, the initial and the final, it equals the velocity of 2, initial and final. This is not a trivial thing to find. Like the video on it's like a 7-minute derivation or something, 5-minute derivation. So it's really, really cool. If you add up the velocity of object 1, its initial plus its final, in this exact problem, it equals the final velocity, initial and final. And that's not a trivial thing to show. It's not like I can just show you all that in 2 steps. It's a whole process to find that. But it's cool. If we had known this, our problem would have been so much easier to solve. If we had known this, we could have set up the relationship. Let's just do the problem that we just did. We could have said that 10 plus V1 final equals 0 plus V2 final. So we could have said that V1 final equals V2 final minus 10, and then we could have just chucked that in this equation, and it would have been way easier algebraically. But to build this, it's a whole process. Watch the video if you want. It is kind of cool. I'm just not going to spend the time on it, hence the video. Okay. Boom, boom. Okay, don't forget X and Y are independent. Let's see. We got 8. Yeah, see if y'all can build the equation. Look, you all know this is going to be true. So let's just jump kind of to step 3. We'll come back and do our due diligence. Remember, y'all, this is going to split. See if y'all can do it real quick. We'll do it next class as well. Like, I'll work through the whole problem. See if y'all can build this equation. You got 7 minutes. That's plenty of time. Okay, I got a falcon. It's coming down at an angle. It hits a pigeon. They hug each other. What's the final velocity of the pigeon-hawk combo? And we're getting it in vector notation. So we got X and Y, y'all. We are steadily building. We did a problem that was 1D with 2 objects. Now we're doing a problem that is 2D with 2 objects. The final problem I'm going to give you is a problem that's 2D with 4 objects. And just to show you kind of how it builds. We start simple, we go from there. Natural progression. But all these problems are the same. Sum of momentum equals sum of momentum final. It's great. Give you like 1 more minute. Don't even worry about the numbers at this point. Okay, so real quick, let's just build this and then we'll call it good. So it's going to be real straightforward, y'all. M1 V1 initial X plus M2 V2 initial X equals M1 plus M2 V final X. You have your initial condition here. The final condition is they're stuck together and they're going to move. All right, great. That's the X. And then the Y, it's the exact same equation. Look, I don't even have to write it. What a blessing. I just move it down here, and it is okay with that. It's not okay with that. All right. Ooh, get out of here. All right. We're going to move this up. We're going to copy this because it's quicker than writing it. Fine. All right. You just replace all these with Y's. There you go. And then we're just going to write down our givens, write down our missing, and actually plug those numbers in. And that's how we're going to do this problem, y'all. All right, see y'all Tuesday. Have fun with the quiz, energy, problems, all that jazz.